This is on page 1, obviously, of your unit handout. We're going to be looking today at graphs of exponential functions and gaining along the way, I hope, a really deep understanding of what an exponential function means in terms of the behavior of the function, in terms of the behavior of y, or whatever is changing exponentially. And we're going to solve a couple of problems involving exponential growth and decay. This is kind of a textbook definition of what an exponential function is. And I'm not using function notation here. I'm just using y. If you have an equation relating two variables, y and x, and the equation is y is equal to c raised to the x, c raised to the x, that's exponential. C is a number, okay? And I don't want to get into the nitty-gritty here of why this is the case, but c has to be a positive number, okay? Can we take a negative base and raise it to numbers? Yes, but strange things happen because sometimes those exponents result in square roots or fourth roots, and if the base is negative, you can't do it. But sometimes those exponents result in odd roots, like cube roots or fifth roots, and it does work. And as a result, if you have a negative base, the function kind of dances in and out of existence depending on what x is. It's not a very useful idea. So c must be a positive number, and c cannot be 1. The base cannot be 1, because if you had y equals 1 to the x, you just have y equals 1, and that's not an exponential function. Y equals 1 is a polynomial function of degree 0. It's a constant polynomial function. So this is a nice visual here. And we're going to be tripping back to this a little bit later, but in your notes you've got this statement. It may look a little bit different. This statement given, it's showing you the allowable values of c. If this is 0 and this is 1, c is not allowed to be 0, not allowed to be 1, but it can be any number in between them or bigger. And depending on where c is, if c is between 0 and 1, the exponential function has a certain property that's different than the property it would have if c is greater than 1. Okay? So those are examples of exponential functions. 1.35 to the x equals f of x, y equals 2 to the x, n of x equals 1/2 quantity to the x. So as a warm-up here, we're going to graph a couple of exponential functions and talk about the domain and range and the intercepts, if there are any, and whether the graph represents what we call an increasing or decreasing function. And then we have to talk about a horizontal asymptote, because exponential functions will always have a horizontal asymptote. Normally I would leave the y column unpopulated in your notes, but to save a little bit of time, it's there. I do want to talk about why these numbers are what they are. Since y is equal to 3 to the x, if I start at the bottom, this would be 3 to the 3, and 3 times 3 times 3 is 27. 3 to the 2 is 3 times 3, which is 9. Notice, well, let's do 3 to the 1 is 3. Notice that every time x goes up by 1, y is multiplied by 3. And that should make sense when you just calmly think about that, because x is how many times 3 is being multiplied by itself. So when I have 3 squared, that's 3 times 3, but if I have 3 cubed, that's 3 times 3 times 3. That's an additional 3. By definition, when we take a look at x being 0, 3 to the 0 is 1. Anything to the 0 is 1 other than 0. And just with that rule, you can see that it matches this pattern, that if you go up by 1, y is tripled. And I don't want to spend too much time on this, because this is basic exponential behavior that you should know from even math 9 or 10. Well, not with the negative exponents for 9, but in 10 you learn that something like 3 raised to a negative exponent is the reciprocal of 3 raised to the positive exponent. You remember that? Well, you got to know it now. If you don't remember it, we need to know that in this unit. That a negative exponent, in the most general sense, I'll write this down for you, that a raised to the negative b is the same as 1 over a raised to the positive b. That's the definition of a negative exponent. And maybe in grade 10 you don't get into why that's the case, but it certainly makes sense here, because If I use negative 1, 3 to the negative 1 is 1 over 3 to the positive 1, which is 1/3. And you can see that that multiplication of 3 is still occurring. When you go from negative 1 to 0, you're adding 1 to x, but the y coordinate goes from 1/3 to 1. And what I want to impress on you, we could go the other way too. If you go in this direction, I guess we would divide by 3 because you're losing 1 each time. What I want to impress on you is that base, which we've called c, is what I refer to as a factor of change. It's what y gets multiplied by regularly. And by regularly, I mean every time x goes up by 1. And once you have that under your belt, once you understand that this will always be a point when you have c to the x, because x at that point is 0, and any non-zero number raised to the 0 will give you 1. Once you understand that if the base is 3, things get tripled, you no longer need this table of values. Because you just say, if I go over 1, I'm going to triple the old y coordinate, it will become 3. And then when I triple it again, it becomes 9. Are you with me on this? We don't have room to go to 27. I've got the data point there, but in the table of values, but we don't have room. Now, we have an issue going in the other direction, and I want to just clean this up. That was just me teaching and writing down what I was saying. As you go backwards, and by backwards I mean in this direction, what's happening here is you're dividing by 3, right? You're adding 1 each, pardon me, you're taking away 1 each time, going in that direction, and you're dividing by 3. So if I take this 1 of the y coordinate here, the y coordinate there is 1, and I divide it by 3 by moving to the left, it becomes 1/3. And the question I want you to consider is, will I ever reach 0 if I keep going back to the left? And the answer is, I can't reach 0. I'm going to reach a number that's, well, not reach. I'm going to keep getting closer and closer and closer to 0 very rapidly. Exponential, one of the ways that exponential is kind of described is it's a very rapid change, either forward or backwards. It keeps increasing as you go to the right at a greater and greater rate of increasing as you go to the right, and it keeps decreasing when you go to the left at a greater and greater rate of decreasing. So I'm even hesitant to put a point over here at negative 2, comma 1/9, because it's going to be just too close. But as a result of that, we are going to have an asymptote here. You were introduced to the concept of an asymptote last year, and I know it might be a distant memory, but it had to do with what we call reciprocal functions. And an asymptote is a line, and we may have even encountered it, well, we did encounter it with tangent functions in the last unit. Those were vertical asymptotes. This is a horizontal asymptote. And the equation of this horizontal asymptote is y is equal to 0. That's the equation of the asymptote. And when we sketch this, you want to draw a smooth curve that keeps getting closer to that asymptote. But do you see that you run the risk of just touching the asymptote if you try to draw it? So I generally don't. What I generally will do, I have to draw it left to right, that's the way my brain works. I generally just do that. I just put a little arrow on the end. The asymptote is drawn, so it's pretty clear what's going on here. I don't think you want to start plotting a whole bunch of points. It gets too close too quickly. Are we okay with that graph? Okay, so what is the domain? Well, the domain is x is any real number. If it's 3 raised to the x, you can take 3 and raise it to any number you want. Are you with me on that? I'm getting the impression that this isn't typed out there, so you have to write it down. Because I hear a bunch of paper being shuffled, and you're looking for, where do I write this down? You're just going to write it down. You're just going to write domain equals that. Whether you even write the word domain is up to you. That's your package for your learning. The range is y is greater than 0. Not greater than or equal to, but greater. The graph will always be above the x-axis, and it can never touch the x-axis because of that asymptote. As a result of that, there's no x-intercept. The y-intercept, of course, is this. And we could just write the number 1 if you like, but I'm going to use an ordered pair. And the equation of the horizontal asymptote is y equals 0. That's the equation of the asymptote. I'm not saying y is allowed to be 0. That's the equation of the asymptote where the function never touches. So are we okay with that? I mean, if it were 4 to the x, then things would be quadrupling regularly as you go to the right, and being divided by 4 regularly as you go to the left. Okay. Well, what happens then if we have a base like 1/2, and that x is strangely drifting away from where it should be? What happens if you have x to the 1/2? Well, I hope it's clear why this will be a point on the graph. Regardless of what c is, as long as c is an allowable value of c, then the y-coordinate there will be 1. I hope it's also clear that if you take 1/2 raised to the 1, you get 1/2. And if you take 1/2 squared, you get 1/4. 1/2 times 1/2. So what's happening to y is it's being multiplied by 1/2 regularly. And at this point, we can abandon the table of values. I'm really hesitant to even include it in this second warm-up, second part of the warm-up, because all we have to do in moving to the right is multiply the previous y-coordinate by 1/2 every time x goes up by 1. And as we go to the left, we have to divide by 1/2, which is doubling. So that means this thing is the opposite kind of pattern. As you go left to right on this, it increases exponentially. As you go left to right on this, it's going to decrease exponentially. And you can make a note to yourself before we even draw this, and think carefully about what I'm going to tell you, that the severity of the changes in this is not as great as the severity of the changes here. Forget about whether it's going up or down, left to right. This involves a tripling in one direction. This only involves a doubling in one direction. It's doubling in the opposite direction because it's 1 over. Of course, we're going to have an asymptote. It will be a horizontal asymptote. The equation will be y equals 0, and we can sketch it. Don't worry if your sketch isn't beautiful. It's difficult. I usually have better success if I do it on a flat surface, but you get the idea. Don't forget to put arrowheads on the top and the bottom of your function. So what can we put here for domain, range, all that stuff? Well, everything's basically the same, isn't it? I mean, the domain is still x is any real number. The range is still y is greater than 0. There's still no x-intercept. The y-intercept is still at 1, and the horizontal asymptote still has an equation of y equals 0. And I think if you think about it, that's going to be the case whenever we have y equals c to the x. As long as c is an allowable value, which means it's positive and not 0 and not 1. Okay. Are we okay with that warm-up? Just to give us a flavor of what's going on. So the first one in the warm-up we call an increasing exponential function. In mathematics, whenever we talk about whether a function increases or decreases, we are always looking left to right. So if this were a hill and you were walking left to right, your height would be increasing. Whereas if this were a hill and you were walking left to right, you would be walking downhill. So this is an increasing exponential function, and it will happen whenever the base is greater than 1. A decreasing exponential function is going to happen whenever the base is between 0 and 1. And I'm going to ask you now to flip pages back to the previous page, because this graphic is a little bit different, but it's the same thing, right? You can add now these two phrases to what's going on here. So from now on, if you were told there's an increasing exponential function, then you need to know that the base is greater than 1. Whereas if there's a decreasing exponential function, the base will be between 0 and 1. I just want to check what time this class ends today. Okay. All right. What function of the form y equals c to the x is represented here in this example? You confirm that this is the graph you're looking at in example 2? This question is not an exam question. You simply have to ask yourself, what's happening to y when x increases by 1? And whatever y is being multiplied by when x increases by 1, that number, that factor of change, what I've called the factor of change, is the base. Well, to go from 16 to 4 means you're going to multiply by a quarter. This is the equation of the function. There's nothing wrong with you writing 0.25. Are you with me on where I'm getting a quarter from? By the way, you can just tell looking at the 16 and the 4 that the number 4 is involved. And since it's decreasing, it's 1 over 4. If the graph is reflected across the y-axis, which is a horizontal reflection, what will the equation of the function become? Well, it will become f of negative x. I hope you see that if I reflect this across the y-axis, that it is going to become that. Would you agree? Okay, let's keep that in mind. This will now become 1/4 raised to the negative x, which is the reciprocal of 4 raised to the positive x. And I hope you can see by looking at that graph that I drew that the rate of change is going to be tripling by a factor of 4. Any questions with B? Okay, so there's a different word we can use or phrase we can use rather than saying an increasing exponential function. We can say that it's exponential growth. So if we have a graph that's exponential and y is increasing, maybe y is the population of mice in an old abandoned barn, and it's increasing. So we call that exponential growth. So certain investments, population of bacteria or people, there are lots of examples of exponential growth that we're going to be looking at. If you have a situation where c is between 0 and 1, that's a decreasing, we can call that exponential decay. So if there's 1,000 mice in this old abandoned barn and I let loose a family of cats, then what you're going to see is the number of mice in the barn over time will go down, and it will probably go down exponentially. And that's called exponential decay. Is there anybody here who has completed Physics 30? Okay, never mind. This happens when you have a quantity y decreasing, so it could be, when you buy a new vehicle, what happens is over time the value of it starts going down. It's usually exponential. Radioactive decay, which we will learn about in this unit and you will learn about extensively if you take Physics 30, is also an example of decay. So we can go back now to that page and add this. I'm just pointing out that this graphic is a really nice graphic to summarize what the base of an exponential function is allowed to be, but it also distinguishes between different types of applications or different types of graphs. So if the base is greater than 1, the function is increasing graphically, but that has an application called exponential growth. If the base is between 0 and 1, the graph is a decreasing graph, but that has applications called exponential decay. You know, the word decay, don't let that fool you. If the number of mice is decreasing because I've let loose a family of cats, and I say the population of mice is experiencing exponential decay, I don't mean the mice are decaying. Right? That's not what I mean. I just mean the number are decreasing. One final note here, if you do happen to go to your textbook uses C for the base, your formula sheet uses B. I like C better because B already has a meaning in terms of horizontal parameter that is the reciprocal of the horizontal stretch factor, so it can get confusing. You have to look at the context. If you see a number at the bottom and they want to call it A or B or C or D, who cares? It's just the base. Example 3. A radioactive sample of radium, and the symbol for radium is Ra225. It happens to be radium-225. And you take physics 30, you'll learn there's different types of radium. But I want to include this here because you might see notation like this on an exam. You might see carbon-12 or magnesium-28 or something. That number is not a number you're going to use mathematically. It's just part of the name of the isotope. It has what's called a half-life of 15 days. And even though this isn't a physics class, you need to know what half-life means. Okay, from now on. Sometimes you are told, but often you're not. A half-life of 15 days means if you start off with a certain amount of radium-225 and you wait 15 days, you'll only have half of it remaining. The other half will have changed into something else. And if you wait another 15 days, it will be cut in half again. I hope you understand that it isn't that you have a certain amount of radium-225 and that amount is fixed and fixed and fixed, and then midnight at the end of the 14th day, it gets cut in half, right? It's a gradual decline like what I have here. So these numbers on the x-axis, 1, 2, 3, are actually 15 days, 30 days, 45 days. And that's why it's labeled time in 15-day intervals. Once again, it means that every 15 days, 1/2 of the radium-225 will no longer be there. It will have decayed into a different type of nucleus or atom. The mass is shown to you as a function of time in 15-day intervals. So now the question, what is the initial mass of radium-225 in the sample? Well, initial means at t equals 0. That's what initial means. Initially means at the beginning. And according to this, at the beginning, it's 1 gram. T equals 0, mass equals 1 gram. What value does the mass of radium-225 approach? The mass approaches 0 grams. Will it reach 0? No in a math class. Yes in a physics class, because sooner or later you'll be down to 1 nucleus and sooner or later it will decay. I'm just pointing that out because I'm assuming many of you will, how many of you are taking Physics 30 next semester? So many of you are, holy smokes, many of you are taking Physics 30 next semester. But mathematically we can say that. What are the domain and range? Well, we want to be careful here because I guess I lied to you earlier. I said the domain of any function of the form c to the x is any real number. But we can't have a negative time here. So you have to write out the domain in the context of the question. The time can be greater than or equal to 0. You can talk about the time at the beginning or the time later, but not before 0. We can't go back in time here and have a negative time. What is the range? Well, the maximum value of m is 1, the minimum value, there is no minimum. It will always get smaller and smaller. This is a bit of a brain buster. There is no minimum, but there is a boundary that it approaches. So this would be your range. It can be anything bigger than 0 for m. The mass can be anything bigger than 0, because mathematically it never reaches 0. Or it can be anything as big as 1, including 1. All right. Write the exponential decay equation. That's it. That's all. If we wanted to construct a graph where t was actually the number of days, that's different, okay? And the only reason this works is we happen to have 1 gram to begin with. So, quite often, we do not have 1 to begin with. I hope you would agree that it's pretty rare for something that's going to experience exponential growth or decay. It would be pretty rare to have 1 as the initial value. I told you that you buy a new vehicle and its value decays. You don't buy a vehicle for $1. The initial value is not going to be 1. I told you that the population of mice in a barn, left alone, might increase exponentially. Well, first of all, if there's 1 mouse, it's not going to increase exponentially unless the mouse happens to be carrying babies with it, right? But it could be 100 mice to begin with. Who knows what it is? So we have to be able to fix that and also fix what's talking about here. Rather than using x, we use t. So if we use t, this is what your function becomes, right? You with me on that? Okay. Once again, and I explained this because I thought it came first, but once again, most of the time the initial amount does not have a value of 1. But this function will have a y-intercept of 1, and that means it's a useless function for applying exponential growth or decay. The y-intercept is not 1 in most cases. So this is what we want to go towards. This number 1 might be down here, right? Well, how can we take a graph that looks like that and make it look like that? The answer is we can stretch things horizontally or vertically. You cannot shift it up, because if you shift it up, that asymptote goes up, and it still has to approach 0. So we fix this problem by multiplying c to the t, which is our basic exponential function, with a y-intercept of 1. We multiply it by some number a, and that means the new y-intercept will be a. It's a vertical stretch by a factor of a. That is a very important equation to know. Now, there's a variation of this on your formula sheet, but unfortunately we won't get to the full version of the equation until when we return. The bottom line now is this y-intercept will be a. So now you need to associate a with the initial amount of whatever is decaying or growing. This is the quantity increasing or decreasing, whether it's number of mice, value of a vehicle, value of a rare coin, value of money in an investment account. T is the time it takes. It's the number of applications of whatever C is. So if C is doubling, it's the number of times things get doubled. Okay? I want you to make a note that C and T are variables, but A and C, pardon me, Y and T are variables, but the other two things are parameters. Right? When you look at the graph has Y as a variable and T as a variable. That's always the initial amount of the quantity, and this is the factor of change. Okay? Do you understand what I mean by the factor by which things change? What was the factor by which things change in our very first example today? 3. In the second example, 1/2. All right, so now we're going to do one final example. And that will leave you with, I believe, about 10 minutes to practice some of these. The current population as of right now of Allentown is 75,000, and the population is decreasing by 5% per year. Per annum means per year. Annum is, I think, a Latin word, and it's where we get the English word annual from. Okay, so it just means per annum. And very often you see it written this way. You see where it says Brementown has a population of 10,000 and is increasing at 9% per A. You need to know that's per year. The symbol for a year in math is A, which I hope that's really not going to be a problem because we also have an A here. We've dealt with this kind of issue before, right? They're obviously not the same thing. Write exponential functions for the population of each town. We want functions that are functions of time. And the time is measured in years. So I'm going to go out on a limb here and hope that you remember this from Math 20-1. If the population, we'll go with Brementown, is increasing by 9% every year, what do you do to the population in 1 year to get the population in the next year? Let's just do a quick exercise on our calculator. Take 10,000. I can even give you a table of values here. This is in years. This is in people. I would like you to find the population after 1 year. It increases by 9%. So whatever you need to do on your calculator to determine the population 1 year later, I would like you to do. Yes? I'm going to guess that most of you would have found 9% of 10,000 and then added it to 10,000. Am I right? Okay. Let's go one more. And I said I hope that you remember this, but it was clear when I said that and I looked out at your faces, you didn't know where I was going with this. So we're going to do it this way. I would like you to now find out the new population 1 year after that, which means we have to find 9% of the current population and add it. To the 10,900. 11,881. What do you multiply each of these by to go forward? Well, that's a basic problem. Mark? 1.09. It's a basic problem where you can just take one population and divide by the population before. You did this with geometric sequences in series last year. This is where this comes in. And the answer is 1.09. So the base is 1.09. Why is it 1.09? This is something you would be expected to explain on a written response. It's 1.09 because you start off with 100% of the population and you're adding 9% to it. If I add 9% to the price of an item, you're going to pay the original 100% plus the 9%. You're going to pay 109%. And 109% in decimal form, which is what you do with percent to multiply it and use it, is 1.09. What would the base of our exponential function be here? And we don't want to do this tabular approach all the time. We have to abandon that. Who can tell me what the base is going to be? Noah? 0.95. Because it's 100% and you're losing 5%, so you're left with 95%. and 95% in decimal form is 0.95. The functions are the population of Allentown as a function of time is 10. Was Allentown 10,000? No. Yeah? Allentown is 75,000 times the base raised to the time in years. The population of Brementown as a function of time would be the 10,000 times 1.09 to the t. And this is just the first layer in this. When we get back, we'll continue to add other layers to exponential growth because we might have situations where it's not every year but every 6 months or every 5 seconds, and we have to incorporate that somehow. So that's the answer to the first part of this question. Are we okay with that? Okay, good. What Allentown is doing is it's starting at 75,000 and it's decreasing. I don't know why. Zombie apocalypse, bad economy, who knows? Brementown is starting down here at 10,000 and life is great. Economy's booming, people are moving in, everybody's having babies. So that's what's happening in these two things. This is 75,000, the initial population of Allentown. Brementown is only 10,000. And that leads to the final question. How many complete years of population change is it going to take for Brementown to surpass Allentown's population? I do not mean how many years will it take Brementown to reach a population of 75,000. I mean, if this is Allentown decreasing at 5%, and this is Brementown, I just want to throw something your way. Do you agree that there is a severity to how rapidly Allentown's is decreasing? I'm going to exaggerate it, but Brementown's will be increasing at a greater severity because it's growing by 9%, whereas Allentown's only losing 5%. And that's something you have to be able to recognize. What we are interested in here, everybody, is that. We're interested in where these intersect. We're interested in where 75,000 multiplied by 0.95 to the t is equal to 10,000 times 1.09 to the t. There is an equation that you would have to solve. But without understanding logarithms, you cannot solve that algebraically. So we have to take a graphical approach. We have to graph y1 equals y2 and find the point of intersection. So what do we have going on here? 75,000 times 0.95 raised to the x. Well, I didn't really mean to put that. You don't need brackets around the 0.95 because your calculator knows the order of operations is you do the exponent and then you multiply. I mean, you should know this does not mean take 75,000 times 0.95 and then raise it to the x. Okay? It means, and I will put it in here just for your gratification if you like, it means that, right? But you don't need those brackets. And then I also want to put in 10,000 times 1.09 raised to the x. And I want to set up my window settings. I don't want to go zoom standard. That's not going to do anything. So let's talk about y first. We know that the population of Allentown starts at 75,000. So it would make sense to go from 0 up to maybe 80,000. You can go up to 75 if you like. You can probably go up to 65, but I'll go 0 to 75 to 85 rather. Okay. And I'm going to put a tick every 10,000. Now what about this? Well, we have to use a bit of common sense here. I mean, we can even go back and look at this table we generated for Brementown. I mean, after 2 years, it's only gained a little under 2,000. So I might guess let's go to 20 years. Let's see what happens in 20 years. I honestly don't know. I just pulled that number out of thin air. You're not going to break your calculator by guessing and then guessing wrong. You can always change it. Up by 5. So I graph. There's Allentown. It's decreasing. I don't think maybe 20 years isn't enough. No, it will be. And I think because I have that bouncy ball, it's kind of wobbling up and down. I just forgot to remove that feature earlier. So there's the answer to the question. We find the point of intersection. And it's 14.65. I got to change this question. So what's the answer to the question? 15. It said after how many complete years? So at 14 years it hasn't happened yet, but at 15 it has. So the answer is 15 years. What if we would have done this and you got 14.01? It's 15. By the way, we didn't need to do that. Because these are up by years of 1, you could set your table up